Hey team, let's talk about SVM, which is called support vector machines, right? Again, this is a part of machine learning algorithm, and SVM is one of the supervised machine learning algorithms, basically majorly used in the world of classification of data. It can also be used in regression, but majorly used in classification, right? So why do we need support vector machines? There are just so many machine learning algorithms already. Why one more, right? SVM is basically very important and effective in handling high dimensional data and non-linear data, right? So we'll talk about what is high dimensional data. We'll talk about what is non-linear data. The objective of this is more to talk in terms of mathematics, right? So that's what we're going to focus on. So basically, to understand how SVM works mathematically, right? We need to understand few of these preliminary methodologies, right? To begin with, what is constrained optimization? So things like if there are constraints, right? Let's say, for an example, you are hosting a birthday party and you have unlimited budget, so which is unconstrained, right? But if you're hosting a birthday party and you have constraints, like you can only order for $100 and things like that, so you have constraints, right? So such data is handled very well by SVM, and that's why we use something called as a constraint optimization, right? And such data sets we need something called as a Lagrange multipliers. We'll talk about that as well. And there are instances to handle such kind of optimization. We also need something called as a KKT methodology, right? And then in KKT, there are 4 different types of things that we do: primal, dual, and a couple of more. We'll talk more about that as well, right? And then the last one is how do we, if it's a linear data set, right? Then all of this KKT and all that can perfectly work. But if it's a non-linear data set, then how do you take care of it? So we introduce something called as kernel functions, and then we'll talk about linear classifiers mathematically as well, right? So before we go into the details, we first need to understand why we need SVM, right? Like I said, SVM is a optimization thing, right? So look at this chart here, right? You have data sets which are in blue over here, and then you have data sets which are in red here. So how do you really classify which is class A versus class B? So as I said, it's a binary thing, right? So how do you really classify? So basically what you need to do is you will need to draw a hyperplane. Hyperplane is nothing but it's a best decision boundary. So think in the lines of it's a straight line in the terms of y is equal to mx plus c, which has a slope and things like that, right? So that's basically hyperplane. We'll also look into how you can draw a hyperplane in SVM, right? Or in classification, basically. The other thing is there's something called as support vectors, right? So the support vectors are nothing but they are the data points which are pretty close to the hyperplane. So over here, this is the hyperplane, right? This line is the hyperplane. And then the dots here that you see, right, are support vectors, which is very close to the hyperplane. So those are support vectors, right? And then margin is nothing but the distance between the hyperplane and the nearest data points from each class, right? So these are the nearest data points, the red ones, right? And then here's your hyperplane. So this is the distance, this is the margin. That's what it is, right? So this is all if it's kind of linear data, right? But if you have non-linear data, then we use a concept called kernel trick, and in kernel there are multiple types: linear, polynomial, RBF, and sigmoid. We'll talk more about that as well. So that's how margins are done, right? So let's take an example. If it's non-linearly separable data, right? So let's say an example, you have the data, right? This is data 1, data point 2, data point 3, right? These are all, say, colored red. But say you have another set of data which is blue colored, right? So these are evidently linearly separable data. So all that we spoke in the top will perfectly work if it's linearly separable, right? But let's say if you have blue over here as well, here as well, here as well, and then you have red also here. So which means there's overlap, right? So it's non-linearly separable. It's just not separable if you look at it, right? So we use a concept of soft margin and hard margin and things like that. So we'll talk more about that. There's a parameter called C. We'll talk more about that, right? Basically, why we are doing all of this is basically we want to optimize this, and we want to see how we can separate the data class so that we can classify, so that we can run it through our algorithms and things like that, right? So that's why we are doing this. So let's take an example over here. Let's take an example. You are planning to build a house, right? And the goal here is you want to minimize the cost. You want to keep it within your budget. And then you want to make sure that it is meeting your requirements of say 30-40 site or whatever that is, right? So basically you use this, and then all that I said are all your constraints, right? So that's the function that you see, min of f of x, which is nothing but the function that needs to be minimized, which is minimize your cost. That's your f of x, right? And you want to keep that within the limit. So that's why you see gi of x, which is nothing but you want to keep it within your budget, and then hg of x is nothing but to again meet your constraints and match your requirements of equality conditions, which is to keep it in a 30-40 site, right? So again, now we spoke about constraints. So there are two types of constraints here, right? If it's an unconstrained thing, then no problem at all. But if you have constraints, there are two problems here again. One is the equality constraint, and then other one is an inequality constraint, right? Equality constraint in a very, very simple term is nothing but it's a part of, like example, x plus y could be f of x, right? Now, if you want to minimize f of x as x plus y, subject to the constraint, say g of x, is say x1 plus x2 is equal to 0. So basically, it's a part of that straight line where x and y kind of are in the equality constraint. But let's say, an example, the same equation, you make it less than or equal to 1, right? Which means your line could be either on +1 or it could be -1, right? So basically there's some inequality which needs some mathematical relationship. So we'll talk about both the examples in terms of equality constraint and inequality constraints, right? For that, we now will introduce two more concepts. We'll introduce a concept called Lagrange multipliers, which has two concepts in it, right? So Lagrange multiplier is nothing but it's the way to optimize your, let me say, optimize your data set that has constraints, right? So think about it this way, right? We have linearly separable data set, we have non-linearly separable, non-separable data set, and then you have constraints, and then in that you have two types of constraints: equality constraint, inequality constraint. Now, for optimizing the constraint data set, you need something called Lagrangian, right? And this is the formula of Lagrangian, which is min f of x, and then you see that over there. Now, you will now see two more parameters there. One is the Lagrange multiplier, which is Vj, and if there's an equality constraint, then you use Vj. And if you have an inequality constraint, then you use lambda. We'll see into an example of both of these multipliers, right? Now let's take an example of equality constraint numerical problem, right? So the objective here is minimize f of x of y is equal to x squared plus y squared, subject to the condition h of x of y is x plus y minus 1 is equal to 0. Take this as an example, something like, say you are building the house. Let's consider building house as x squared plus y squared, which means you have $100 and you have a 30-40 site, right? You can build that f of x at that minimalistic cost subject to equality constraints, which is you should have a 30-40 land and you should have $100, something like that, right? So once you have that, you kind of do 6 steps. The first step is form the Lagrangian, which is nothing but introduce the v parameter that we just spoke about. So your f of x now becomes x squared plus y squared plus v x plus y minus 1, right? Once you're done that, the step 2 is we'll have to do partial derivatives and set them to 0, right? So that's just a form of the part of the equation. So how you do derivatives? You do derivative of L to that of derivative of x. So basically rest of all will be muted. X will be the derivative. So x squared plus y squared plus vx plus y minus 1 will become 2x plus v is equal to 0. Likewise, you do for the derivative of y. So again, everything will be muted. Y will get a little empowered, so it becomes 2y plus v. Likewise for the third one, derivative of L given to that of derivative of v will become x plus y minus 1 is equal to 0, right? So once that is done, you will need to solve these equations. You can use, reduce row echelon form and whatnot. So basically what happens is, or in this, it is very simple, right? So 2x plus y is equal to 0. So you move v is equal to minus 2x. Likewise, you do v is equal to minus 2y. So basically v is nothing but minus 2x minus 2y. which implies x is equal to y, right? And then you substitute x is equal to y in the third equation, which is x plus y minus 1 is equal to 0. So 2x is equal to 1, x becomes 1 by 2. So since x is equal to 1 by 2, x is equal to y, so y obviously becomes 1 by 2. And now you substitute that, you will get the v value, right? So basically your optimal solution x comma y is 1 by 2 comma 1 by 2, because that's x comma y, right? Now once you have that, you substitute that into your minimized function, which is f of x comma y is x squared plus y squared. So you put that over here in step number 5. Once you do that, you get the value of f of x comma y. Then you substitute x is equal to 1 by 2, and you substitute into v is minus 2x, so you get the value of v as well, right? So the Lagrangian multiplier v is equal to minus 1. This is what we want, right? So we calculated everything, and you found the value of x, you find the value of y, and you also found the value of the Lagrangian multiplier, which is v, is minus 1. So basically what it says, it's minus 1. So it indicates that even if you slightly change the objective function, you change the constraint a little bit, the objective function will change, right? So that's how you do this. For instance, if we change the constraint to x plus y minus 1.01 is equal to 0, objective function will increase by approximately minus 1 into 0.001. So basically, you can see the effect of changing the parameter of Lagrangian multiplier to that of the objective function, right? So that's how it is done. And now this is for equality, but let's say you have inequality constraint, right? It's a bit complex. So we introduce another thing called as KKT, and only if the KKT conditions are necessarily met, only then the optimality is achieved, right? So what are the KKT conditions? There are 4 conditions. The number 1 is stationarity, primal feasibility, dual feasibility, and complementary slackness, right? We'll look into what each of it means, but basically what stationarity means is the Lagrangian with respect to the decision variable x is equal to 0, right? Then we also talk about primal feasibility and dual feasibility. So you might be wondering what it means. We'll talk more about primal feasibility and dual feasibility, and then we'll also talk about complementary slackness in the upcoming slide. So first we'll look into a numerical example, and then we'll talk about what's primal, dual, stationarity, and complementary slackness, right? So let's begin with minimizing. So the problem statement here is it's a inequality constraint. The objective here is like you see x squared plus y squared less than or equal to 5. It's just not equal to 0. So it's kind of an inequality constraint. So the question here is minimize f of x of y is equal to x squared plus y squared subject to constraint. And we want to verify, this is a problem statement where we want to verify the 2 points, whether they are in the optimal classification or not, right? So that's what it is. So again, step 1 is from the Lagrangian. So here we won't use v, rather we'll use lambda. So L of x comma y lambda will nothing but x squared plus y squared, and use the lambda term, which is plus lambda that of x squared plus y squared minus 5 from the equation above, right? Then you do KKT conditions. You take the derivative of with respect to x. You do the same with y, and then you realize that 2x plus 2 lambda x is equal to 0. So it meets the condition of stationarity, which is derivative of x, derivative of L with respect to x, and derivative of L with respect to y should be equal to 0. So it meets the stationarity condition, right? Primal feasibility says that your equation x squared plus y squared minus 5 should be less than or equal to 0. So over here also we'll figure out if we are getting that, right? By substituting the values of x and y. So we know what is x. We know x is 4 by 5, and y is 8 by 5. So we substitute that in this formula. We'll realize that it is actually equal to minus 1.8, which is less than or equal to 5, right? So what we're doing here is this particular formula, we are substituting these values, and we are finding out this, and this proves that it is less than or equal to 0, so it meets the condition. Likewise, dual feasibility, we need to find out what's the value of lambda, and we need to prove that it's greater than or equal to 0, right? So that we are doing here. Before that, the stationarity condition, we just have the derivative 2x plus 2 lambda x is equal to 0. So we substitute the values of x and y. We already have that. Once we substitute, we realize that the value of lambda is equal to minus 1, right? Likewise, we do the same for the other one. We find out lambda is equal to minus 1, which means that stationarity condition fails. And dual feasibility says that lambda should be equal to 0, greater than or equal to 0, but it's minus 1, so it fails as well. The last condition is complementary slackness, which nothing but it says that the lambda value should be is equal to the lambda x squared plus y squared minus 5. The Lagrangian part of it should is equal to be 0, right? Over here we see that it is actually 0. So sorry, over here we see that lambda x squared plus y squared minus 5, substituting value of that, lambda minus 1.8 is equal to 0. This implies either lambda is 0 and we found that lambda is above minus 1. So we can see that x squared plus y squared minus 5 equates to minus 1.8. So basically this condition is also violated, which means that 0.45 comma 8/5 doesn't satisfy KKT condition because it violates all of these, right? So what do you mean by primal feasibility, dual feasibility, and things like that, right? Let's start with primal feasibility. Primal feasibility, nothing but the data set stays within the rules. Example, you're planning a party, you have a budget of 100, which is your constraint number 1. You need to invite 3 people, say 10 people, that's your constraint number 2, and you want to buy or order 2 pizzas, constraint number 3, right? Primal feasibility says that all of these constraints should be met. Party should be within $100, should have at least 10 guests coming in, and you should buy 2 pizzas, right? If any one of these is violated, it violates the primal feasibility, right? So what is dual problem? Dual problem, nothing but the same party, you have a third party consultant come and tell you, I can organize that for you, and I give you the 3 different offers, right? The first offer is the price that you'll pay will be you pay $1 less if you don't spend all of your money. So basically you save money, the consultant gives you back money, right? The second thing is the price they'll charge you for every guest below minimum of 10. They'll reward you or penalize you based on the number of guests that come in. Likewise for the pizza, right? So dual feasibility basically ensures that whatever you plan, you kind of stick to that, right? You get rewarded for for the right behavior or having fewer guests and things like that. So basically that's what dual means, right? So basically we know what is primal, we know what is dual. So complementary slackness tells us if the resources are fully utilized or not, right? And it rates it active or inactive. Basically that's what complementary slackness does. Stationarity is the last one, which is nothing but it's the condition for optimality, right? It kind of tells if your points, the Lagrangian, based on the Lagrangian function, if they are giving you a potential optimal solution, right? So that's stationarity. Now let's move on to like I earlier showed you, right? Different type of data. There is linearly separable, there is linearly not separable. So this is what I kind of showed you before, right? Now if you have a linearly non-separable data, we introduce a term called kernel. So kernel basically what it does is it helps the SVM as an algorithm to handle non-linearly separable data, right? And we come up with a concept called kernel trick. This one, what I'm going to do is I'm going to explain you more like in layman terms. Let's say an example, you have say 10 coins, right? 5 red coins and 5 blue coins, right? Now, if you just put it on a table, probably you can't, if you put it on the table, you can probably draw a straight line that perfectly separates the red coins versus the blue coins, right? But what if, we put them in a circle? So you basically can't, say 1 red, 1 blue, 1 red, 1 blue in that ways, right? So you cannot really separate them. So it's non-linearly separable, right? So what the kernel trick does is you move the plane to a hyperplane. You lift it to a higher dimension, right? So basically what you're doing is you're just throwing, say, those coins high up in the air. And then when it's in the air, you kind of be able to naturally separate them into 2 distinct groups. And then you can say these are linearly separable, right? But throwing that, the act of throwing and all that is called transformation, but it's really not feasible when it comes to data, right? So that's why we have a shortcut called as kernel function. So instead of actually throwing those coins or throwing those marbles on the trampoline, we perform this a transformation using kernel function shortcut. So it's nothing but it's just a way of doing a dot product of 2 similar vectors and coming with the outcome. So we'll talk more about it in detail in the upcoming slides, right? So what is SVM? Like we want to separate the data set, right? So the primary objective of SVM is nothing but It's a hyperplane, as you can see. This is the hyperplane. This is a 2D example. So we want to separate the data points between the classes. All right, so here what we want to do is we want to basically maximize the margin, right? So let's say an example of the hyperplane is wx plus b is equal to 0, right? And then the blue dots and the red dots are nothing but your support vectors which are close to the hyperplane, and the distance between the support vectors and your hyperplane is nothing but the margin. So that's what it is explaining. Now basically what we want to do is we want to maximize the margin. So what it means is you want to make sure that your margin is as big as possible so that the classification of data is as appropriate as possible, right? So that's what we're going to talk about in the next slide. So you want to maximize as much as possible the margin, and this is basically done in linear SVM. So we'll talk about other few different types of SVM as well, but we'll start with linear SVM, right? So the math that we follow here is we want to find out, or the goal here is we want to maximize the margin between the two classes of data points and to find that hyperplane, right? So let's take an example, simple example of a line y is equal to mx plus c. We equate that in a hyperplane format. Wx plus b is equal to 0, where w is the weight vector, x is the input data vector, and b is the bias, right? So you draw the margin boundaries. The margin is defined by two parallel hyperplanes, which we saw in the previous slide. One is the plus positive side of things, and the other one is the negative side of things. So wx plus b is equal to plus 1, and wx plus b is equal to minus 1. The margin is nothing but, in mathematical terms, it is the norm of w. So m is nothing, margin is nothing but 2 divided by the norm of w, which you can also equate it as 1 by 2 to the square root of the norm w, right? So that's what maximizing margin mathematically means, right? So moving to the next slide, basically that's what maximizing margin does. It 2 divided by root of w, or is equal to 1 by 2 to that of w squared, right? So that's what we do, and then what we are doing here is we want to prove that the maximizing margin, we want to prove it through the 5 steps that we did previously, which is your primal problem, Lagrangian, KKT conditions, and then we want to find out what are the W and B, and then prove that by doing this you are getting the needed maximized margin, right? This is a good example of a support vector algorithm. So here you have let's say three data points, x1, x2, and x3. So x1 and x2 are in the minus scale, and the x3 vector is in the positive side of things, right? So and then the equation, these are all given, right? These are all given when asked. So this equation 1 is summation of alpha I yi xi dot x plus b is equal to 1. The second, when it's positive, when it's negative, it's minus 1, and then your alpha I yi is equal to 0 is given, right? Now it's given an assumption that bi is equal to alpha I yi. So which means that if bi is alpha I yi, then ai yi is nothing but bi is equal to 0, right? So we replace ai yi xi with bi, or b1, b2, b3, b4 in this case, right? So basically, if you look at it, let's do an equation for x is equal to x1, right? So because it's in the minus side, this minus 1 comes here. So what you're doing is you're taking this equation over here, the second one, and you're expanding the summation, which is b1 x1 dot x1 plus b2 x2 dot x1 plus b3 x3 dot x1 plus b is equal to minus 1. Likewise, you're doing it for x2 as well, which is 2 comma 1, and you're expanding this equation. The third equation, you see a plus 1 here, and guess what? Why? Because this is in a plus classification segment, right? So you use this this formula. So b1 x1 dot x3 plus b2 x2 dot x3 plus b3 x3 dot x3 plus b is equal to 1, and then obviously your summation of alpha I yi is equal to 0, which is nothing but alpha summation of bi is nothing but b1 plus b2 plus b3 is equal to 0, right? So that's where we are. So you got this equation. So the next step is we'll have to plug in these values, which is x1 dot x1. So x1 dot x1 is nothing but 1 comma 2 comma 1 comma 2, which is nothing but 1 into 1 plus 2 into 2 is equal to 5. So x1 dot x1 is nothing but is equal to 5, right? So likewise you do x2 dot x1, right? x2 dot x1 is nothing but 2 comma 1 1 comma 2, which is nothing but 2 ones are 2 and 1 2s are 2, which means 4. So this b2 x2 x2.x1 becomes 4, right? Likewise, you do the math. So substituting all these values, you become 5b1 plus 4b2 plus 12b3 plus b, and likewise you get all these equations, right? So once you get these equations, you do RREF, reduced row echelon form, and basically you will find these values, right? So b1, b2, b3, and b value you get. Now once you get these values, obviously the next step is you substitute that in the equation that we had before, which is bi xi. So you substitute the values of 0.08, 0.08, 1.6, and you get the value of x1 and x2, right? Basically that's how you do it. So you get the values of x1, x2 is equal to 5.5, so which is nothing but your line. That's the straight line, the best fit line. W dot x plus b is equal to 0 is x1 plus x2 is equal to 5.5, right? And then we also know what is our x1, x2 value. We also know what those support vector x3 is. So basically you are able to separate the positives against that of a negative by drawing this hyper plane line, right? The red, the one that is over there. So that's how SVM is done. Now, the more the data set you have, you can draw this line and segregate non-linearly separable data in a view that I'm showing right now, right? So that's how it is done. So that was more in the terms of linear SVM. Now, say for example you have a non-linear SVM. Basically, instead of a straight line, say you have curved boundaries, and say something you have overlapping. Like I said, these are all say reds, and then you also have blues inside this. So it's overlapping, right? So how do you transform that? So for that, we will need to do some transformation. Mathematically, how we do it is we come up with the optimization formula, which is nothing but, and introduce a function of kernel, which is k over here. So this is a mathematical formula. We just need to remember this. So goal here is for in SVM is to find a decision function f of x that classifies the data point correctly. In linear case, it's pretty straightforward, but in non-linear case, you will need to use the kernel function and do stuff like that, right? You can read through this. Basically, it's imagine you have data that can't be separated by straight line. Then you use the kernel trick. It's basically you throw something in the air, find that transformation and mimic that, and that's nothing but kernel trick, right? Here are the steps. Select a kernel function, compute the kernel values, you get the kernel matrix, and then you get the new value. Basically, you want to predict what, if a new data set comes, which data set they are classified into, right? So that's basically what you do in a classification use case. So once that is done, these 4 steps are done, you'll be able to find out the new data set. Is it in the upper part of the the graph, or in the bottom part? So that's how you do it. Here's a numerical example. Let's take an example of 2D data set where there are 2 classes, class plus and class minus. Class plus has x1 values and x2 values, likewise x3 and x4 values. Here the kernel function is given. Here we are using a simple polynomial kernel of degree 2, right? Likewise, you can use any kernel function, which we'll talk. There are 4 types. We'll talk more in the upcoming slides. So let's take an example, kx, x1. So that's the kernel that's given. Kx, x1 is equal to x dot x bar plus 1 the whole square. So we'll have to obviously compute the values of kx dot x bar, which could be kx1, kx1, x1, kx1, x2, likewise till kx4, x4, right? So you substitute these values and you get these values here, right? And then you take all of these values and that becomes nothing but a kernel matrix. So once the kernel matrix is done, obviously you do reduce row echelon form and whatnot to find that out. But before you do that, this is an assumption that is already given in the problem statement. We've given the values of alpha 1, alpha 2, alpha 3, alpha 4. And then like the problem statement here given was, say you get a new data set, you get a new example. Say x is equal to 1.5, 1.5. So you'll have to classify which class it will be, whether it'll be in class +1 or whether it'll be in class -1. So that's the ask, right? So here we compute the kernel function. So again, we take this formula kx, x1, kx, x3. From the previous example, we compute 16 and 20.5. Now we use the decision function, which we covered as a part of the kernel trick. There's a formula that you need to have. Substitute the values of alpha I, y1, kx1, x1, and likewise, you get f of x is minus 24.25, which means it is in negative. So f of x is negative, we classify this as class -1, right? So that's a numerical example of how you use non-linear data set and how you can do kernel function and get the answer. Like I said, there are types of kernels. There are 4 different types of kernels, and the kernels are basically classified based on the nature of the data and things and different features, right? RBF kernel is usually used if you go into Kaggle or any of those portals. If you do any search for a classification problem set using SVM, you usually will see RBF values set there. But you can also do, RBF is nothing but radial basis function or Gaussian kernel. You can also do linear kernel. We also saw a polynomial kernel of degree 2 in the previous example. You can also do sigmoid. Here are some differences in terms of when to use what, right? So that's pretty much about it. But if you want to look at a numerical example of a XOR problem, basically this is a data set which evidently you can see that it is linearly inseparable, right? So you look at it, there are 4 dots, they are in different 4 quadrants. Basically you can't draw a line. So that basically it's that problem, right? So again, this is an XOR problem. So you do kernel trick, you do dual formulation, you do Lagrange multipliers, you find out the support vectors, and then you find the W, and then you find the bias. Remember that WX plus C component, right? Or MX plus B component. So you find the bias, and then based on all these mathematical things that you do, you'll get something called as a decision boundary that will tell you where the data, where is that hyperplane? Like, is it here, or is it here, or is it here, or wherever that is, right? So basically, once you do the math, it will tell you that. I'm not going to go through all the steps, but just at a high level, if you look at it, start with the kernel. So this is something that you assume basically, and then this is because it's given, you then expand this. This is nothing but using the formula of a plus b plus c, the whole square is equal to a square plus b square plus c square plus 2ab plus 2ac plus 2ca, that kind of thing, right? So that's what is done here, and then you substitute the values with x1, x2, x3, x4. You compute that to that formula that was given in the previous slide. Then you find the resulting kernel matrix, which is listed here, which is step 1 is done with this. Then you do step 2, which is dual of SVM. We know the formula of the dual objective of SVM. This is the general formula. You substitute these values that you have in the matrix, you will find this. Then you'll have to do the Lagrange, which is step 3, using the formula using the derivatives of q over lambda alpha I. You get this, and you'll find out solving this equation, you'll get 1 by 8, which is alpha I value. Once you find that out, you need to find out the step 4, which is support vectors and weight. You substitute the value of what you found over there, and you find out the distance, right, which is W naught squared. And then the step 5 is nothing but you find the bias, which is again, this is all substitutions. I'm not going to go through it. You find the bias value 0, and based on that, we realize that we substitute the values of, we know what's the value of W transpose psi x, and we also know bias is 0. So once you substitute all the values, you get the answer x1, x2 is equal to 0, which is nothing but y is equal to minus x1, x2, right? And now you know what the values of x are, minus 1, 1, which we saw in the previous slide. Now you multiply minus 1 into minus 1 into minus 1, you get y is equal to minus 1. Likewise, you do, so you get this new predicted value of y, right? So that's your decision boundary. That's pretty much it when it comes to support vector machines. Any questions, feel free to ask me. Thank you.